And if the initial concentration of A is 1m, what's the rate after 1 hour? Okay? So this is not really that hard. You just have to put down things, see what you have and what you need to find. So let's put things down first, right? We have rate constant to be equal to 5.0 times 10 to minus 5 second minus 1. The initial concentration of A is equal to 1 mole per liter. And we want, after 1 hour, what's the rate? So we want the rate at time t when t is equal to 1 hour. That's what we want to have, right? So always do that. Always when you have problems, do that. Translate your problems into this part. Otherwise, you're wasting your time. Okay? And now, you know that if you want to find out the rate at some time t, you know that that rate will be equal to the rate constant times the concentrations to the order, right? But it tells you it's first order in A. So it's going to be A, that's it. And you can put that t there to just make it specific. A lot of authors, they don't do that, and it's confusing. When you say rate at time t, it means that concentration, not initial, not any concentration, at that time t. At that time t, with this concentration, the rate is that. So, if we want to find R at time t, we have the rate constant, we just need to find out what? The concentration at time t. So, do you know the concentration some other time? At 0, yes. And therefore you go to the equation that you will have in the back diagram. So you know it's first order, right? So, it is first order. You will know to recognize the equation. That's another thing, right? First order will give you natural log of A at time t. It will be equal to minus kt plus natural log of A at time 0. So from this one now, you know that you know everything. You can find out the concentration of A at time t. Minus, you have to be careful with the signs and the numbers. So from this one, you find out the concentration of A at time t is equal to 0.835. And therefore, rate at time t is going to be equal to rate constant times 10 to minus 5 times 0.835 is equal to 4.2 times 10 to minus 5 molar per second. So the answer is B. Right? The other one is a good one. The other one does not have concentration, it's pressure. I mean, pressure, it's in concentration. But you know, when you talk about pressure, right, so many times you can express the rate of the reaction as a function of pressure instead of molarity. Why? These two things are proportional. You realize that, right? How many people want me to show you why they're proportional? Pressure and molarity. Let me see your hands. How many people want me to show they're proportional? Pressure and molarity. Let me see your hands. Isn't it? So you can see at constant temperature, this is a constant number, so pressure is proportional to molarity. So instead of talking about molarity, when we have gases, we can talk about pressure, because it's proportional. So we can express the rate of reactions, right? It's a function of change of pressure, not concentration. These are proportional. So let's say a problem in regard to this. So you don't really know what it is, you have to really find out now. So you just have to do a little bit of work. It's not easy to see immediately. If you can see it immediately, great. But so what you know is that the rate of the reaction is, by definition, right? By the definition, the rate of reaction. We didn't say appearance, nothing. It talks about oxygen, so I'm going to express the rate of the reaction according to the general definition of rate of reaction, general reaction, right? It's a function of the concentration change of oxygen, right? So the rate will be equal to, oxygen is produced, it's going to be plus, there is one coefficient there, 1 divided by 1, and then I'm going to put change of concentration of oxygen, brackets means molarity, divided by delta T. And I can clean it up, make it look pretty, without signs and 1, 1. So the rate, according to definition of this reaction as a function of change of concentration of oxygen, is going to be this ratio right here. Okay? Now we can see there's pressure there. So I have to get rid of the molarity and put pressure. How are you going to do that? Well, you saw that. So what are you going to do? Let's relate the two, right? The pressure and the concentration, right? So from this, you saw before, you actually can say pressure of oxygen is equal to the molarity of oxygen times RT, isn't it? So if I substitute the oxygen there, so I need to solve for oxygen from here, right? Concentration of oxygen, which is the same thing as MO2, isn't it? That's why you have to be careful with symbolism, right? It's the same thing, but you need to realize it, right? It's going to be equal to pressure of oxygen, solving from here, right? Times RT to minus 1. And so now if I go to my equation here, rate, as you saw from there, is equal to this. Therefore, now I'm going to put the whole thing, delta, P oxygen, RT minus 1, divided by delta T. And now notice, the problem says that it's a constant temperature, some temperature, right? T, some temperature T. That means it's constant. So if this is constant, then I can take it out of the delta, right? So I can say only delta T divided by delta T, and it's supposed to be oxygen. So right, it doesn't say there. Times RT minus 1, and therefore the answer is